Hello everyone, welcome to my YouTube channel. In this video, we are going to discuss how to select a database for your distributed service. Nowadays, you can find a large number of database technologies. Having such a large number of products and technologies means having more trade-off decisions to make. Given that each database product is optimized for certain scenarios, it rests on the software architects and senior software engineers to pick appropriate database with these trade-offs in mind as it relates to the requirements of the service. Choosing the most appropriate database based on the requirements of the service is one of the most important architectural and system design decision. Because later if you find that the selected database is not appropriate for all your requirements, then migrating to another database is very costly and risky process, and it could take a lot of time. Choosing an appropriate database is not based on a simple decision tree where you can just decide simply that if we have structured data, then we will use relational database. If we have a semi-structured or unstructured data, we will use maybe something like NoSQL. And also it's not as simple as saying that since we need ACID requirements, we will choose relational database. And if we don't need ACID requirements, we can live with eventual consistency, for example, then let's choose a NoSQL database. There are multiple different criteria that we have to actually go through in parallel, and we have to decide after going through all of those criteria, and we have to weigh different choices of databases that we have, that how those databases will fulfill all those criteria or requirements that we have, and after that we have to come up with an appropriate database for our service. You also need to understand that sometimes you may be in a situation where you will have to choose between two databases and none of them is appropriate for your requirements. But in that case, you have to see which of the database among these two databases is more appropriate as compared to the other for your requirements. Before discussing different types of databases, now let's discuss what are different criteria that we use to select a database based on the requirements of our service. The very first criteria is ease of learning curve. This criteria refers to the ease with which new developers, architects, DBAs, and other users of the database can learn and adopt the use of a particular database. Most developers tend to select the database which they have already worked on in the past and have some experience of, or if they think they can easily learn that database easily. Choosing a database based on past experience is okay if it fulfills all the other different criteria that we are going to discuss now, and also it fulfills all the different important requirements of your service. The second criteria that we use to select a database is the database product maturity and technical support. This characteristic refers to how mature the database is, what is the size of the database community, and how easy it is to hire someone with that database experience. It also sometimes refers to how many and which programming languages the database support. We can take relational database like Oracle database, for example. This database has been here for more than 5 decades, and we can easily find a lot of documentation on the internet about it. There's also a lot of different communities on internet that we can find on Facebook or other communities where people have worked on relational databases. And so it's very easy to get some help from the community if we need in a relational database. The third criteria that we use to select a database is based on our data model or schema of our data. The data model or schema is one of the most important criteria for choosing a database. This signifies that our database is chosen based on how well it can provide support to the software developers to model and store the data of the service. Data can be structured like SQL schema, or semi-structured like a JSON or XML object, or it could be totally unstructured data like, for example, some media files, some images, some videos, audios, etc. The data could be relationship data. For example, in case of Twitter system design, we have a follower and follower relationship. Or it could be a friendship relationship in case of, let's suppose, Facebook. Choosing the right database for the right model is also a very important key system design decision. The fourth criteria for choosing a database is scalability. This criteria refers to the degree and the ease with which a database can be scaled to support increased load and throughput while minimizing the data access latency. It means that while choosing database, we have to see whether the database can be scaled horizontally, vertically, or both. This also relates to the volume of data that needs to be stored in our service. Sometimes the volume of data is small enough to be stored in a single machine, but then other times the volume of data could be so huge that it cannot be stored in a single machine. Another important criteria to select a database is the query and data access pattern. This criteria refers to whether a system is read-heavy or write-heavy, and so the database is selected to prioritize either read over write or write over read if needed. This is not a binary choice, but rather it is more of a scale towards which direction the database optimizes. Then another very important criteria for choosing a database is the cost. Sometimes you see two different databases with almost similar capabilities. In this case, it depends on the overall cost associated with using each database, based on which you select one of the two databases. This cost comprises of several expenses. For example, the cost of buying a database license, maybe it's a one-time license or maybe it's a subscription. Then there's a periodic maintenance that needs to be performed on the database. During the periodic maintenance, is there a downtime that the service need to incur or not? Also, what would be the cost to hire people who have experience with such a database? Another important criteria to select a database is based on whether your system needs ACID requirement or your system is a base system. The ACID, where A stands for atomicity, C stands for consistency, I stands for isolation, and D stands for durability, is a set of properties of a database transaction intended to guarantee data validity despite errors, power failures, and other mishaps. In the context of a database, the sequence of operations that satisfies the ACID properties are called transactions. For example, transfer of funds from one bank account to another bank account. This would involve multiple sequence of operations. For example, debiting money from one account and crediting money to another account. And all of these operations need to be done within a single transaction to make sure that your system state remains valid. On the other hand, the base systems are those systems which do not meet the ACID properties. It does not mean the base systems lack all the different ACID properties. There could be base systems that fulfill some criteria of ACID properties. For example, a database will be considered base if it fulfills properties like atomicity and isolation. Similarly, there could be a base database system that fulfill durability and isolation, but not consistency. However, one thing is guaranteed for base systems, that they always prefer availability over strong consistency in a CAP theorem. The base systems are always eventually consistent, as the name suggests. So now the choice of database depends on whether the system requires an ACID compliant database or not. Ideally, every system wants ACID properties. However, the ACID properties, though very desirable, are not always possible to achieve due to other non-functional requirements imposed by the system, which affect the choice of a database. We just discussed what are different criteria to select a database. Now we will go through different common types of databases that are available right now, and we will see what are their pros and cons before going through an example in which we will see how we will choose a database in a particular example or scenario. The very first type of databases which are available since more than 5 decades are relational databases. Some examples of relational databases are Oracle database, MySQL, Microsoft SQL Server, etc. Relational databases are based on relational model, which is very intuitive and straightforward way of representing data in the form of tables. In relational databases, each row in a table is a record with a unique ID called the primary key. The columns of the table holds different attributes of the data, and each record usually has a value for each attribute, making it easy to establish relationships between different data points. Relational databases allow flexible data modeling. The relational databases even allow modeling of key value data and graph data, which we will discuss later in our other different types of databases. However, it does not mean that a relational database can be used in all the scenarios. It depends on several factors to decide whether a relational database is a good fit for a particular scenario or not. Relational databases are generally vertically scaled using large machines. This is one of the limitations of the relational databases because sometimes the data in the system could be so huge that it cannot be stored in a single machine. There are other scenarios as well, where even if the data can be stored in a single machine, the number of read and write queries that come to a database are so large that they cannot be handled by a single machine. In that case, the only option that we have is to shard a relational database. But usually relational databases does not support implicit sharding. The sharding needs to be done manually in that case. And also, usually when we shard relational database, then we store the data in the sharded relational database in a shared nothing architecture, which means that all the data for a particular tenant we store in a single shard. We does not distribute the data for a single tenant in all the different shards that we have created for our relational database. Another limitation of relational database is that they have usually a rigid schema. Changing the schema of a relational data in a relational database requires changing the table construct in the relational database. Thus, changing the schema in a relational database is usually a painful, time-consuming, and thought-provoking process. That is why in such cases we have to look at other different database types such as NoSQL databases that we are going to discuss now. Before we go into discussion about different types of NoSQL databases, I have a question for you guys. Let me know in the comment below whether the relational databases can be distributed or not, and if yes, how, and if not, why not. Now, another type of a very common data store that is used in different services is a key value data store. A key value data store is the simplest form of a NoSQL database. It is similar to a hash table data structure, and it is primarily used in scenarios where all access to the database is through a primary key. The key value data stores are a preferable choice when all the access to the data is through a primary key. The relational database constructs like joins or where or order by are not required as they are not supported by the key value data store. When the scalability is an important requirement of the system, and since key value data store allows easier scaling and higher throughput, the key value data stores can easily be sharded using consistent hashing. We also use key value data store in scenarios where database schema is flexible and whatever we store in the blob value is opaque to the database and only understood by the application. It doesn't mean that if the key value data store is a NoSQL data store, it does not support ACID requirements. There are different key value data store that offer ACID requirements, but usually most of the time they offer those ACID requirements only for a single key operation. That is operation which only touches a single key. Also, we need to understand that the consistency in a key value data store is a bit different than the consistency in a relational database. And the consistency in a key value data store is associated with the replication of a key value data to all the nodes or replicas in a shard. Usually the key value data stores are good fit for following scenarios. The first scenario is about storing session information. Generally, every web session is unique and is assigned a unique session ID. Applications that store the session information on the disk or in a relational database will greatly benefit from moving to a key value data store. Almost every user has a unique user ID and then some attributes like username and other information. All this information can be stored in a key value store. In order to get access to that information, we only just need a unique user ID and that's it. Another scenario where key value stores are a good fit is a shopping cart scenario. E-commerce websites usually have a shopping cart tied to a specific user. In that case, in order to quickly retrieve the shopping cart associated with a user, we can use key value data store to store the shopping cart information. And we can access the shopping cart using a unique ID of the shopping cart that could be associated with the user ID as well. At the same time, we also need to understand different scenarios where the key value data stores are not a good fit, such as if the application need to have relationships between different entities and objects in the data, then the key value data store is not a good fit. Another scenario where the key value data store are not a good fit are the scenarios where we have to query or scan a large amount of data. Key value data stores are usually optimized to query data based on a primary key. And now if we need to run a query in which we are scanning a large amount of data, key value data stores are in that case not a good fit for such scenarios. Also, the key value data store does not support searching based on the value. That is, if we want to search some data based on particular value in a data, we cannot search using a key value data store. Some examples of key value data stores include Redis, Memcache, Oracle Coherence, Amazon DynamoDB, etc. Now the second type of a NoSQL database is a document database. The basic unit of storage in a document database is the document itself. These documents are usually self-describing hierarchical tree data structures, usually stored in the form of either XML, JSON or BSON, etc. Nowadays, the most popular format used is JSON. The documents stored in a document database could be similar to each other, but they do not need to have exactly the same format. The document database are like key value databases, which store documents in the value part of the key value data store. However, we can consider document databases as a superset of key value data stores where the value is not opaque to the database and database can examine the value content, which is not the case in a key value data store. Now the question is how the document database is different from relational database. We need to understand that in a relational database, all the records need to have same schema and they need to have same set of attributes if we are storing them in a single table. While in case of a document database, different documents can have different schema. Also, as compared to the key value data store, there is one difference, which is basically in case of a document data store, we can create secondary indices on different attributes of the document, which is not possible in case of a key value data store. The document databases are a good fit for the following scenarios. Since document databases have no predefined schema and usually understand JSON documents, they work well in content management systems or applications for publishing websites, managing user comments, user registration, profiles, and other web-facing documents. E-commerce applications often need to have flexible schema for products and orders, as well as ability to resolve their data models without expensive database refactoring or database migration. Document databases are suitable for such scenarios. The examples of document databases include MongoDB, CouchDB, and Azure Cosmos DB. By the way, I have added a detailed chapter in my course, The Distributed System Design Interview Bible, that you can find the link here, in which I have discussed all the different types of databases, their pros and cons, and different scenarios where we can use them for more information. Now there is another type of databases which we use in some specific scenarios, which we call column family databases. These databases are sometimes also known as wide column databases or big table databases. These usually have rows with varying number of columns, where each column is a name value pair. The column family databases allows access to data based on columns rather than by rows, and even sometimes they store the data by columns. There is a class of databases which we call columnar databases or column-oriented databases. This is a subset of column family databases in which we store all the data in column-wise as compared to row-wise in case of other types of data stores. When a column family data store is also column-oriented data store, then the benefits include more efficient access to data when we are querying only one or few columns, that is a subset of columns. And there's also more options for data compression in case of a column-oriented databases. However, the column-oriented databases are less efficient for inserting new records. The main difference between a column family database and a document database is in the query model. They can both store similar data structures. That is, you can actually store a JSON in a column family database as well. But the document stores usually give you query by value capability, whereas column family databases usually do not. Another difference between a document database and a column family database is that in the document database, you usually insert or update the whole document, which is typically a JSON. Whereas in column family databases like Cassandra, you can address individual columns and insert and update them individually. So the columnar databases are a good fit for scenarios where you only need to query a subset of the columns or very few columns. Also, we use columnar databases in scenarios where you need to run aggregation queries against a large amount of similar data. On the other hand, the columnar databases are not suitable for scenarios such as online transaction processing scenarios or in scenarios where you have to run queries against a small set of rows. Some examples of column family stores are Apache HBase, Cassandra, and Google's Bigtable. Here I have two questions for you. The first question is that usually column-oriented databases are more suitable for analytic scenarios. Why is this the case? And the second question is, the column-oriented databases usually provide better compression. Why is this the case? Let me know in the comments below what you guys think. Another type of database which is getting popular day by day is graph database. The graph databases represent data as graph, which is nothing but a network of nodes and edges between them. The edges between the nodes actually represent relationships between those nodes. In a graph database, the storage is optimized for storing the graph and also is optimized for graph traversal. We can store a graph-like data structure in a relational database as well, and also in some NoSQL database like DocumentDB, etc. But those databases are not optimized for running the queries that require traversing the graph. And so the graph databases are more suitable for such scenarios where we have queries which require traversing the graph, as we will see later. Now let's discuss one scenario and let me know in the comments below what do you think, whether we can use graph database in such scenario or not. So in one of my previous video in Twitter system design, which you can find the link here, in one of the microservices, we defined a user relation table. Since in our design we are only required to query a single hop relationship, that is find all the followers of a particular user, and also the relationship is of a single type, such data could be stored in a relational database. Another option is to store this data in a NoSQL key value database, which provides a non-unique secondary index on the followee user ID. Storing such data in a graph database, although possible, will be an overkill usage of graph database. In this case, the only reason for storing such information in the graph database is that either we plan to introduce more relationship types, or we plan to introduce multi-hop queries like find all the followers of a particular user, or find all the followers of a user A who are also the followers of user B in the future. So that's why you need to understand that even though you might be working with some data which require graph traversing, or I would say some sort of graph traversing, but using a graph database for such scenario may not be that useful if the relationship between all the different entities is just a single type of relationship and the queries that you are running only require a single hop relationship. The graph databases are usually used in following scenarios. The first scenario where the graph databases are being used a lot is fraud detection in payment systems such as Stripe. With a graph database, you can process purchase and financial transactions in almost real time, which means you can prevent fraud. For example, with a graph database, you can easily detect whether a particular email address and credit card are related to other fraudulent charges or not. You can also differentiate accounts where a single email address is associated with multiple people. You can also find scenarios where various people are associated with a single IP address, even though they have multiple physical addresses in different accounts. Another usage of graph database is in recommendation systems. For example, in Facebook, the graph database can be used to store information about various users and their friends and their interest in a social graph. This graph can be traversed to suggest friends and other services to a user. There are other social network and machine learning and AI scenarios where the graph databases can be used, which I have covered in more detail in the course. One thing to remember is that the graph databases are not suitable for scenarios when the queries don't include a specific starting point. For example, if you need to run frequent table scans, then graph databases are not suitable for such scenarios. Also, when you need to look up a single data just by a key, in those cases, graph databases are not suitable, and you may be well off with using a key value data store in that case. Also, the graph databases are not suitable for scenarios where you have to store large chunk of information and such as blobs and media files, etc. with every node. Let me know in the comments below, why is this the case? Why the graph database is not suitable for such scenarios? Then there is another class of databases which we called time series databases. These databases are optimized for storing and serving time series data. A time series data is some data which is associated with a timestamp. The time series data is often continuous flow of data like measurements from sensors in IoT or intraday stock prices. A time series database lets you store a large amount of time-stamped data in a format that allows fast insertion and fast retrieval to support complex analysis on time series data. Here we need to understand that Relational databases can also be used to store time series data, but relational databases are not optimized for common time series workloads. We have discussed in greater detail how a time series database stores time series data in a format which enables quick retrieval of timestamp data as compared to other traditional databases in our course. And then lastly, there is a new class of databases which we call new SQL or distributed SQL databases. You can consider new SQL databases as relational databases with implicit support for sharding and scalability. And these databases are more suitable for financial systems and other systems like, for example, billing service in Amazon or Apple App Store, where asset requirement is a must, but also the scale of data is so big to be stored in a single machine, or the throughput required is so big to be handled by a single machine. Now let's consider a scenario. You must have seen my previous video on designing TinyURL service, which you can find the link here. In that service, in one of the microservices, we come up with this schema where we want to store a URL mapping between a short URL and a long URL. Now the question is, what type of database do we need to store this information? So the very first thing is that we will always start with a relational database and check whether we can store this information in a relational database or not. And in that case, we have to first decide whether the data is structured data, is semi-structured, or is totally unstructured data. And it's totally possible we could say that this could be a semi-structured data. What we could also do is that we can store all this information in a single blob field or glob field in a relational database. So a relational database could be of the format where it has only two columns. One is the ID column and the other is a blob or glob field where we store the rest of the information, and that could be another unstructured information from the perspective of a database, and we use relational database for this purpose. However, now we have to see how much data are we going to store, let's say in the next 6 months or a year or 2 years, which means that we need to figure out what would be the growth of data that we are expecting in the system. And then the second thing is, what would be the query load? What would be the rate of writes? What would be the rate of reads that would be happening? And can we use a relational database in that case or not? And of course, since it's a TinyURL service, we know that it's a read heavy system. The number of writes will be way less as compared to number of reads in the system. We will only perform the writes when we want to actually insert a new short URL to big URL mapping in this table, for example. We could also maybe think about other things, like we can still use the relational database. So in that case, how to actually support scalability, we could do some other things. For example, we can still use a relational database in our service, but we can actually put a cache in front of our relational database to support heavy read. So now it all depends on the types of requirements. What are the different requirements we have in our system that can be fulfilled by a particular type of database or not. Now let's just take an example that we also want to introduce something like a count here. And it's an integer. And let's suppose this is the count of read access to this database. And suppose this is now a requirement, which doesn't even make sense basically, but let's suppose you want to also see how many times a particular short URL was accessed. So every time now the read happen and someone tries to get the big URL using a short URL, you also incrementing this count. Initially the system was a read heavy system, but now since with every read you are also updating this count, so now this system becomes a write heavy system basically. And now you have to think what would be the best database in that case, whether it's a relational database or it is a key value data store that you would use, or you will use a document data store or a column value data store. If we use a relational database here, or even if a document database, whenever we update this count, what we will be doing, we will be updating the whole record itself. In that case, it would be way better if we use a column oriented database, because in a column oriented databases we access and store based on columns. So in that case, whenever a URL get read, you can just go and update the count of it without touching the rest of the data. Now let's take another example. Suppose we have a graph of different objects and entities and their relationships. the objects or the nodes are different types of nodes. We have people in the nodes. We also have like things like banana, and we may also have cities like Berlin. Similarly, the types of relationships are also different. We have friend relationship, we have a follow relationship, we have like relationship, we have visit relationship, etc. In this scenario, where we have different types of entities and they have different types of relationships between them, the graph databases are the most suitable choices. Of course, you can store this information in a relational database as well as the document data store as well, where you can actually store this follow, likes, visits, all different types of relationships in a relationship column. And maybe it might work with some simple queries, like if you want to say, give me all the users which Jason likes, for example, which is a single hop query. It may work in a database. If you want to run some complex queries like, give me all the followers of Jason friends, then graph databases are best fit in order to run such type of queries. So let's summarize again what we have discussed in this video. So the first thing we discussed is that we can't just come up with a simplified decision tree based on whether we need structured data or semi-structured or structured, whether we need acid properties or not. And then based on that, we can just say, we can just use relational or a particular type of NoSQL database. Usually in that case, we have to construct a complex matrix actually, or a table to determine which database is more suitable for our scenarios. People usually think that we can't use relational databases for unstructured data, but that's not the case. As long as you can actually access your unstructured data using an ID. You can define a table with just an ID column and a blob or glob column. And you can store all your unstructured data in that glob column in a relational database. So this is a wrong assumption that you can't use relational databases for unstructured data. You can, but basically you have to look at other things. So relational databases are, I would say, are always the preferable choice. You should always start with a relational database. For example, if you are working on a product catalog service in Amazon, for example, where you keep track of all the different products. Now, different products will have different attributes. Or baby infant milk will definitely have different attributes than a TV or some other electronic devices. So now if a data is semi-structured, what is the best place to store it, whether it's a relational database or not? Usually here one other thing is that if the data is unstructured data like a media file, a video file, then usually we store them in object storage service and we just store the URI for those objects in our databases. We usually don't store big blobs in our database, because every time you update an attribute, you will also be writing that big blob of data as well, and which is usually bad for the database performance. We see that relational databases, you can just shard them as well, but then you have to shard the relational database manually. And usually in that case, we use a shared nothing architecture to shard those relational databases, where we put all the tenant information in a single shard. Then we have a key value data stores. Key value data stores are like simple hash table data structures, where you have a key and then a value. Value is a blob. In a key value data store, the value is opaque to the database. The database does not look into the values. And so in that case, if you need to also run queries in which you have to look into the opaque value in a key value data store, then the obvious choice is a document data store, because a document data store is like a superset of a key value data store, where the database also can examine the internal data of a value itself. And so you can create secondary indexes on those attributes in the value part in the document DB. Then we also discussed there are certain scenarios where we only have to access, maybe for read or write, only a small subset of columns. And for those scenarios, column-oriented databases are a good fit, basically because you don't have to read or write the whole record or whole row, and you can only access and only update or write the columns you are interested in. Then we also have a graph database, and there are scenarios where the graph databases are the best choices, where these are the cases where you are working with data which have multiple different types of relationships among them, and also you want to run queries which require multiple hops, not a single hop but multiple hops. And so in that case, the graph databases are more suitable choices to be used. If you want to know more about these things, please look into my course. There's a chapter where you will find more details about it, in which I have discussed in detail how to select a database. In the end, again, thanks a lot if you are still here with me. and I will really appreciate if you find this video useful. Then please do like this video, and also do subscribe to this channel if you haven't subscribed yet. I will be adding more videos in future soon. Thank you and take care.